morning students, this is Arvind, Assistant Professor, Department of Triple Device IT Cavali. So in the previous class I discussed about comparison between HPC and STATCOM, that is comes under the third unit of Social Transmission System. And now in this class I am going to discuss I am going to start the fourth unit, that is static series compensation. So the last chapter is static shunt compensation. So in that one we discussed about HCC and STATCOM and the static path systems and the comparison between HCC and STATCOM and objectives of static shunt compensation and methods of controllable wire generation and variable impedance type wire generators, hybrid wire generators, switching wire generators, like that we are discussing. And from now onwards I am going to discuss the fourth unit, that is static series compensation. Okay, so in that one first concept is actually the concept of series compensation. So in that one we have the objectives of series compensation. So today I am going to start the introduction about the objectives of series compensation, and next I am going to discuss concept of static series compensation, like that. So firstly I will start with the introduction to the objectives of series compensation. So actually the reactive shunt compensation is highly effective in maintaining the desired voltage profile along the transmission line interconnection. Okay, so the reactive shunt compensation. So this is the previous chapter. Okay, last chapter discussed. In that one we are using the reactive shunt compensation. So based on this, I will explain series compensation also. So first I will take the overview of the reactive shunt compensation concept. So the reactive shunt compensation is highly effective in maintaining the desired voltage profile along the transmission line interconnection, two buses of the AC system, and providing support to the end voltage of radial lines in the face of increasing power demand. Okay, the reactive shunt compensation is applicable for highly effective in maintaining the desired voltage profile. Okay, along with the transmission and interconnection of two buses of the AC system and providing support to the end voltage of radial lines in face of the increasing power demand. So here, thus reactive shunt compensation, when applied to sufficiently close intervals along the line. So the reactive shunt compensation, when applied at sufficiently close intervals along the line. So this could theoretically make it possible to transmit the power up to thermal limit of the line. So that is theoretically possible, but not practically. So that's why we are using so many methods to transfer the power from one circuit to another circuit. Okay, so the reactive shunt compensation, when applied at sufficiently close intervals along the line, so this could theoretically make it possible to transmit power up to thermal limit of the line. So if a large enough angle between the two end voltages could be established, if a large enough angle between the two end voltages could be established. So however, shunt compensation is ineffective in controlling the actual transmitted power. Okay, the shunt compensation is ineffective. Okay, the shunt compensation is ineffective in controlling the actual transmitted power at a defined transmission voltage is ultimately determined by the series line impedance and the angle between the end voltages of the line. Okay, so here the shunt compensation is ineffective. So in controlling the actual transmitted power with a defined transmission voltage. Okay, so and this will be overcome by the ultimately determined by the series line impedance and the angle between the end voltages of the line. That's why we are taking this series compensation. Okay, so it was always recognized that AC power transmission. Okay, it was always recognized that AC power transmission over long lines was primarily limited by the series reactive impedance of the line. Okay, so here we are using series reactive impedance, okay, in the line, that too for the over long line, that means power transmission over the long lines. At that time we are using the series impedance, series reactive impedance, which will limit the power transmission between the overhead lines, that means the long lines, long distance lines. So series capacitive compensation was introduced decades ago. So actually this concept is already existed in decades ago. But why we are using this series capacitive compensation means to cancel a portion of the reactive line impedance, to cancel a portion of the reactive line impedance and thereby increase the transmittable power. Okay, so the series capacitive compensation is was introduced decades ago. Why? Because to cancel a portion of the reactive line impedance, to cancel a portion of the reactive line impedance and thereby increase the transmittable power. So subsequently, within the FACTS initiative, it has been demonstrated that variable series compensation is highly effective in both controlling power flow in the line and in improving stability. So for the both cases, we are using this series compensation. So that's why I am telling that within the FACTS initiative, it has been demonstrated that variable series compensation is highly effective in both controlling power flow in the line and in improving stability. So for the total we are using the series compensation. And next, so the controllable series line compensation is a cornerstone of FACTS technology. Okay, the controllable series line compensation is a cornerstone of FACTS technology. So it can be applied to achieve full utilization of transmission assets. Okay, it can be applied to achieve full utilization of transmission assets by controlling the power flow in the lines. By controlling the power flow in the lines, that is preventing loop flows. So it preventing the loop flows and controlling the power flow in the lines, and with the use of fast controls, minimizing the effect of the system disturbance, thereby reducing traditional stability margin requirements. Okay, by it can be applied to achieve these requirements. Okay, so that is full utilization of transmission assets by controlling the power flow in the lines and preventing loop flows, and with the use of fast controls and minimizing the effect of system disturbance, thereby reducing traditional stability margin requirements. So now in this session I am going to discuss the basic approach of reactive series compensation will be reviewed to provide the necessary foundation for the treatment of power electronics based compensators. Okay. So now in this section I am going to discuss the basic approach of the reactive series compensation will be reviewed to provide the necessary foundation for the treatment of power electronics based compensators. Okay, that's why I'm going to discuss the mainly the concept of series compensation first, and later I'm going to discuss the objectives of series compensation. So before going to the concept, I am discussing one more point, that is the effect of series compensation on the basic factors determining attainable maximal power transmission, steady state power transmission limit, and transient stability, voltage stability, and power harness and damping will be examined. So by using this series compensation, the effect of the series compensation on the basic factors, we have to determine the attainable maximum power transmission, and at the same time steady state power transmission limit, transient stability, voltage stability, and power harness and damping will be examined. These are the different objectives in the series compensation. So these topics I will discuss later, and firstly I will discuss the concept of series capacitive compensation. Okay, concept of series capacitive compensation. So in the previous chapter we discussed about the concept of shunt reactive compensation, and now in this chapter I am going to discuss concept of series capacitive compensation. Okay. So the basic idea behind series capacitive compensation is to decrease the overall effective series transmission impedance from the sending end to the receiving end. Okay, the basic idea behind series capacitive compensation is to decrease the overall effective series transmission impedance from the sending end to receiving end. So that is X means that is a reactance in the power P that is equal to V square by X into sin delta. So these will give the relationship characterizing the power transmission over a single line, characterizing a power transmission over a single line. So that's why I am taking one diagram. Okay, it consists of simple two machine model analogous to that shown for shunt compensation. So that is in the previous chapter. So in the previous chapter also we discussed one diagram that consists of two machine model along with the shunt compensation. Now in this class I am going to take the same two machine model but with the series compensation. Okay, so here I am taking but with a series capacitor compensated line which for convenience is assumed to be composed of two identical segments. I will show the diagram. So this one, so it is a two machine power system with series capacitor compensation. So here I am taking sending in and receiving in voltages, that is Vs and Vr, and next we have capacitor and reactor combinations. So the capacitor consists of the value that is Xc by 2 and the reactor consists of the value that is X by 2 on both sides. So on the left side actually we have the combination of these two, capacitor and inductor, Xc by 2 and X by 2, and the whole current flowing into the system is I, and the midpoint voltage we have that is Vm. Okay, like that, and we have the power. Okay, this is the two machine power system with a series capacitor compensation. So actually this is the two machine power system with an ideal midpoint reactor compensator. Actually this is covered in the previous chapter, that is the concept of series reactor compensation. At that time we are taking this diagram. So here we are consisting two machines. One is at the sending end and another one is at the receiving end. That is Vs and Vr. It consists of the voltage Vs on the sending end and Vr on the receiving end. And we have midpoint, we have at the midpoint of the system we have ideal compensator. In this one we have the power that is equal to 0 and we have midpoint voltage that is Vm, and on both sides we have the reactance that is X by 2 and X by 2, and we have the currents ISM that is sending end to the midpoint current, and IMR that is the midpoint to receiving end current, and X by 2 is the value of the reactance we are using. Okay, this is for the shunt reactor compensation, and this diagram is for the series capacitor compensation. This is a two machine power system. Okay, so next, so the corresponding voltage and current phases are shown in the diagram, that is in this diagram. So this is the phasor diagram we are using. So in this one I am taking current I and midpoint voltage are in the same phase, and we have to this time we have for both sides we have a sending in voltage and receiving in voltage. So the line drawn to the left side of the Vm, we have the Vs that is the sending in voltage, and the line drawing right side of the Vm line that is the Vr that is the receiving in voltage, and both will have the capacitive compensation value that is Jxc by 2 and minus Jxc by 2, and totally we have the reactive voltage that is Vx. Okay, and we have the current I. Okay, so note that for the same end voltages, the magnitude of the total voltage across the series line inductance, okay, the magnitude of the total voltage across the series line inductance, that is Vx, that is equal to 2 into Vx by 2 is increased by the magnitude of the opposite voltage that is Vc. Opposite voltage that is Vc, it is developed across the series capacitor. Okay, firstly we have the total voltage across the series line inductance, that is Vx. So actually we have the equation that is Vx is equal to 2 into Vx by 2 is increased by the magnitude of the opposite voltage that is Vc, and it is developed across the series capacitor. So this results from an increase in the line current. So the effective transmission impedance, that is X effective, with the series capacitive compensation is given by X effective is equal to, that is effective transmission impedance is equal to X minus Xc, or this will also write as X effective is equal to 1 minus K into X. So here K is the degree of series compensation. So that is K is equal to Xc by X. So this will occur when when K is lies between 0 to 1. Time period 0 to 1. In between 0 to 1, the K, that is the degree of series compensation, exists. So this is the phasor diagram, And next, so here assuming Vs, that is the sending end voltage, is equal to receiving end voltage, and that is equal to total voltage. From this diagram, I am assuming that condition that Vs is equal to VR is equal to V, and the current in the compensated line, okay, the current in the compensated line and the corresponding real power transmitted, okay, the current in the compensated line and the corresponding real power transmitted can be derived in the following forms, that is I is equal to, actually you know the formula is 2V by x into sin delta by 2, so same is in that formula, so I is equal to 2V by 1 minus k into x into sin delta by 2. So previously we discussed this one, that is this one x effective is equal to 1 minus k into x. So right here, that is 2V by x effective into sin delta by 2, that is 2V by 1 minus k into x into sin delta by 2. So from this one we are writing P is equal to, you know already P is equal to, power is equal to multiplication of voltage and current, that is the midpoint voltage into current, that is P is equal to Vm by 2, sorry Vm into I, sorry. So that is equal to, we have V square by 1 minus k into x into sin delta. Okay, P is equal to V square by 1 minus k into x into sin delta. So from this, the reactive power supplied by the series capacitor can be expressed as follows. So the reactive power, that is QC, is supplied by the series capacitor, that is Q suffix C, can be expressed as follows, that is equal to QC is equal to I square into XC. I square into XC. So that is equal to, we know already I formula, that is 2V by 1 minus k into x into sin delta by 2, and XC value, that is k by 1 minus k whole square into 1 minus cos delta. So that is QC is equal to I square into XC, that is equal to 2V square by x into k by 1 minus k whole square into 1 minus cos delta. So the relationship between the real power P and series capacitor reactive power, that is QC, and angle delta is shown plotted at various values of the degrees of series compensation K, is shown in this diagram, that is C diagram. Okay, so this diagram gives the relationship between real power and series capacitor reactive power versus angle characteristics. So here I am drawing the characteristic diagram between power P and the real power P and reactive power Q versus angle delta. Okay, here we have real and series capacitor reactive power at P, Q. So here we draw totally 5 curves we drawn. Okay, so the curves are drawn between angle delta and reactive and real powers of the series capacitor. So that's why I am taking the power P maximum and 2P maximum. So here I am drawing 5 curves. So the first curve is drawn between 0 to pi, that is the delta is in between 0 to pi, and we have another curve that is drawn between same 0 to pi. So when k is equal to 0, 1 diagram, and when k is equal to 0.2, that is 1 diagram we are taking. Okay, for k is equal to 0 we draw 3 diagrams, 3 characteristic curves, that is in between 0 to pi, and one more curve is drawn between 0 to pi, that is not touching the delta value. So that is k is equal to 0.2, and next we draw a curve that is Q suffix SC is equal to 2 into V square by V square into k by k, x into 1 minus k whole square into 1 minus cos delta, that is the reactive power equation, that is QC is equal to 2V square into k by 1 x into 1 minus k whole square into sin delta, that is this one. And we have the curve that TS is equal to V square by k x into 1 minus k into sin delta, that is only for the real power. And we have k is one more curve, that is k is equal to 0.4. Okay, this gives the characteristic diagram between real power and series capacitor reactive power versus angle, that is delta. And from the diagram it can be observed that as expected the transmittable power rapidly increases with the degree of series compensation K. Okay, it can be observed that as expected the transmittable power rapidly increases with the degree of series compensation, that is K. So similarly, the reactive power supplied by the series capacitor, the reactive power supplied by the series capacitor also increases sharply with K and varies with angle delta in a similar manner as the line reactive power. That's why we have these type of curves. Okay. So after deriving the simple relationship characterizing series capacitive compensation, so it should be known that the duality of the underlying physical explanations. So we have to note that duality of underlying physical explanations. So the conventional explanation is that the impedance of the series compensating capacitor cancels a portion of the actual line reactance and thereby the effective transmission impedance per 6 point. That is the first diagram, and the first equation we have, that is this one, x effective is equal to x minus x3. So here this is the cancellation of the particular portion. So the conventional explanation is that the impedance of the series compensating capacitor, that is x value, it cancels a portion of the actual line reactance and thereby the effective transmission impedance, that is x effective, for that one is reduced as if the line was physically shortened. Is reduced as if the line was physically shortened. Okay, next. So an equally valid physical explanation is, which will be helpful to the understanding of converter-based power flow controller, is that in order to increase the current in the given series impedance of the actual physical line, the voltage across the impedance must be increased. So this is another type of explanation. So in this one, it is helpful to understand the converter-based power controllers is that in order to increase the current in the given series impedance of the actual physical line, the voltage across the impedance must be increased. So this can be accomplished by an appropriate series connected circuit element. So that is such as capacitor, and the impedance of which produces a voltage opposite to the prevailing voltage across the series line reactance. Why? Because in the diagram we are using capacitor and reactance both in this series capacitive compensation for a two-machine system. So this can be accomplished by appropriate series connected circuit element such as a capacitor, and the impedance of which produces voltage opposite to the prevailing voltage across the series line reactance. And as the phasor diagram that is shown in the diagram C, illustrates thereby causes this latter voltage to increase. So from this diagram I am telling to this one. Okay, next it is easy to see that within this second explanation, that is the physical nature of the series circuit element is irrelevant. So the physical nature of the series circuit element is irrelevant as long as it produces the desired compensating voltage. Okay, next, thus an alternate compensating circuit element may be envisioned as an AC voltage source which directly injects the desired compensating voltage in series with the line. Okay, thus an alternative compensating circuit element may be envisioned as an AC voltage source which directly injects the desired compensating voltage in series with the line. So as will be seen, the switching power converter used in the shunt connected STATCOM. Okay, as will be seen, the switching power converter used in the shunt connected STATCOM, that is in the previous chapter. In the we are using the shunt connected STATCOM. This one is applied as voltage source in series with the line. So serves the functional capabilities of series capacitive compensation and also provides additional options for power flow control. So in this one we are using this shunt connected STATCOM. This can be applied as a voltage source in series with the line. So it serves the functional capabilities of series capacitive compensation and also provides additional options for power flow control. So that is the concept of the series compensation. And now we are moving to the second concept, that is objectives of series compensation. Actually we have different objectives of series compensation. Those are listed below. Those are voltage stability and improvement of transient stability and power oscillation damping and subsynchronous oscillation damping. So actually the above three. So here we have four objectives. So among these four, we already seen three objectives in the shunt compensation. So here we have one more objective, that is subsynchronous oscillation damping. This is the only objective we are added in the series compensation objectives. So I will explain the voltage stability concept here, and in the next class I am going to discuss the improvement of transition stability and power oscillation damping and subsynchronous oscillation damping. So firstly I will cover this voltage stability concept. So this voltage stability is the key objective of series compensation. So that is, the series compensation can also be used. Okay, the series capacitive compensation can also be used to reduce the series reactive impedance. Okay, series capacitive compensation can also be used to reduce the series reactive impedance. Why? Because to minimize the receiving end voltage, that is VR. So receiving end voltage variation and the possibility of voltage collapse. Okay, next, further I am taking a simple radial system. Okay, simple radial system with feeder line reactance X and a series compensating reactance XC and load impedance Z. So these all combined we have one diagram. I will show the diagram. So this is the diagram. So it gives the transmittable power and voltage stability limit of a radial transmission line as function of series capacitive compensation. So if you observe this diagram, so on the right side we have A diagram, so on the left side we have A diagram. In this one I am taking sending end voltage. So here we are taking one machine, so that is sending end voltage, and receiving end we have impedance, that is Z, and in this one the Z is equal to R, that is impedance is equal to resistance, and we have variable capacitor and fixed reactance. So the variable capacitor is Xc and reactor is X, and the sending end machine consists of the sending end voltage, that is Vs, and the receiving end load consists of the receiving end voltage, that is Vr, and on the right side we have the characteristic diagram. So here we draw the characteristic diagram between receiving end voltage versus power. Both values we are taken in the per units. So the power is taken the per units from 0 to 3 per unit, and the voltage, receiving end voltage taken between 0 to 1. So here I draw three curves. So the three curves is drawn when the capacitor is changes, capacitor reactance is changes, that is when x is equal to 0 we have one curve, and when x is equal to 0.5x at that time we have one more curve, and when x is equal to 0.75x, so at that time we have last curve. So these three curves we draw versus VR and P, and so the corresponding normalized terminal voltage, that is VR versus power P, plot with unity power factor load, that is at 0, 50 and 75% series capacitive compensation. Okay, is shown in the B diagram of this one. So this characteristic diagram. Okay, next. So the nose point at each plot. So if you observe this diagram, so these are the nose points. The arrow mark is there. So these three are the nose points of the characteristic diagram. So the nose point at each plot given for a specific compensation level. Okay, that represents the corresponding voltage instability. That represents the corresponding voltage instability. So note that figure 6.2, that is this one, is analogous to the 5.3 diagram, that is in the shunt compensation objectives, that is in the previous chapter. Okay, where the same radial system with the reactive shunt compensator supporting the end voltage is shown. So in the diagram we have shown that the same radial system with a reactive shunt compensator supporting the end voltage is shown. So this is the diagram. This is the diagram we are used. This is the diagram we are used for the shunt compensation, that is for the variation of voltage stability limit of a radial line with load and load power factor. Okay, and excitation of this limit by reactive shunt compensation on the B diagram. So on the right side, on the left side we have the circuit arrangement, and then the left side we have the right side we have the characteristic diagram. So in the first diagram we are using only one radial line without wear compensator, and in the second diagram we are using wear compensator. Okay, So this diagram is analogous to the previous one. Okay, next. So from that one clearly both shunt and series capacitive compensation can effectively increase the voltage stability limit. Okay, so clearly both shunt and series capacitive compensation can effectively increase the voltage stability limit. So shunt compensation does it by supplying the reactive load demand and regulating the terminal voltage. That is for the shunt compensation. And series capacitive compensation does it by cancelling a portion of the line reactance and thereby in effect providing a stiff voltage source for the load. So for the shunt compensation, what we did for the shunt compensation, it is done by supplying the reactive load demand and regulating the terminal voltage, and for the series compensation does it by cancelling a portion of line reactance and thereby in effect providing a stiff voltage source for the load. So for increasing the voltage stability limit of overhead transmission, series compensation is much more effective than shunt compensation of the same MVA rating. Okay, so for increasing the voltage stability limit of overhead transmission, series compensation is much more effective than shunt compensation of the same MVA rating. So this is the explanation for the first objective of series compensation, that is voltage stability. So in this one we are discussed about the how we improve the voltage stability limit in this one by using the series compensation. Okay, thank you for watching this video, and in the next class I am going to discuss transient stability improvement and polarization damping and subsynchronous oscillation damping concept. Okay, thank you.